In this video and in the other videos that I have dedicated to the notable special limits, I don't want to give you the proof of an analytic result, but I would like to invite you to a visual memorization using plots and thanks to MATLAB, and I would like also to help you in familiarizing with different type of notations that can be used. After these 5 minutes, I would like you to be able to reproduce 3 formulas and to associate them to their graphical meaning. This fact, the connection with the graphical interpretation, tells you how those formulas are actionable. MATLAB has already plotted for us the graphs of the functions y equals sine of x and y equal x, the bisector of the first and third quadrant. I want to compare those lines in the neighborhood of the origin, that is, as x goes to 0. Now, we deal with two infinitesimal functions. Well, indeed, they cross the origin and they are continuous functions. This is not the important things to say. They both go to 0, but I want to specify how they go to 0, how they tend to 0. They tend to 0 in the same way. This is what I want to express. And in mathematics, we have an appropriate symbol for that. The function sine of x, when the variable goes to 0, is equal to the function x plus an error plus a negligible part. But negligible is a relative comparison. Negligible with respect to what? With respect to the function that I have just written, that is, with respect to the function x. Look how the distance between the red function and the green function goes rapidly to 0 as x goes to 0. Here we are. Small o of x means this. It converges to 0 more rapidly than x, so rapidly that can be neglected with respect to x. The function sine of x is equal to the function x plus a negligible part with respect to x. Of course, we're talking of something that happens in the neighborhood of the origin. We use now the fundamental properties that connects the symbols of small o with the symbol of asymptotic. F is equal to g plus small o of g if and only if f is asymptotic to g. We pass now to a writing, to a formula that is totally equivalent. The function sine is asymptotic to the function x in the neighborhood of the origin. The notation that uses small o emphasizes the error. The notation that uses the symbol of asymptotic emphasizes the behavior, the fact that the sine of x, the function red, and the function x, the green one, go to 0 in the same way. At this point, I use the definition of the symbol of asymptotic. Two functions are asymptotic in the neighborhood of a given point if and only if the limit of their quotient goes to 1. We deduce that the limit as x goes to 0 of the sine of x divided by x gives 1. This is the form with which this limit involving the behavior of the sine function in the neighborhood of the origin is usually written. It's a formula that is totally equivalent with respect to the others, but it's maybe less seducing, less appealing under the point of view of the geometric interpretation. I conclude, as x goes to 0, we have found three equivalent ways to express the behavior of the graph of the sine function with respect to the graph of the angle bisector of the first and third quadrant in the neighborhood of the origin. The sine of x is equal to x plus small o of x, emphasizing the error. The sine of x is asymptotic to x, emphasizing the behavior. The limit of the quotient between sine of x and x is 1, emphasizing the analytic result. It's a good idea if you learn all the three of them, because according to the type of exercises we will deal with, one can be more effective than the other. The best thing would be that from the graph you are able to rebuild all the three writings as we have done together.